Okay, so last time we had started on the topic of significant figures, which I will not be very strict about that in this class, but it's good just that you know what it is. And it will give you some guidance on how many digits to keep when you're entering an answer in WebAssign. Again, it doesn't matter, except when the questions are literally about significant figures. So there may be some questions that are like, how many significant figures are there in this? Or, multiply two numbers, keeping track of the significant figures. So if the question is about significant figures, then you have to keep track of it. So the basic idea of significant figures is that it is a quick and dirty way to communicate to someone how confident you are in every digit that you write down when you're giving that number. It is not a rigorous way of doing it, but it's a quick enough way of doing it. And every experimental measurement has associated with it an uncertainty due to various effects, like the limited accuracy of the experimental apparatus, the skill of the experimenter, the number of times the measurement is carried out, that is, reliability studies, can you reproduce the result each time? So the value of a measurement is meaningless if we do not know the uncertainty associated with that measurement. So again, to give you the example, if you say a car is going at 55 miles per hour, you might think you have a sense at how fast it's going, but if then someone comes and tells you, well, they came up with that number by they were on top of a hill looking at the car and they were kind of eyeballing it. So there's probably an error of plus or minus 40 miles per hour. Then it puts that number in a whole new context, meaning that you really don't know how fast that car was going. So here's a simple example of how an uncertainty can arise from the limitations of experimental apparatus. If you try to measure the length of this pencil using a ruler, then in some sense, the spacing between the tick marks provides a limitation on the accuracy with which you can measure this length. And so therefore, this here is measured to be 7.1 plus or minus 0.1 centimeters. Roughly the spacing between, yeah, go ahead. Yes, let's do that. Yeah. So the number of reliably known digits in a number is called the number of significant figures. And the idea here is that you typically only want to write down those digits that are quote unquote reliably known. So you don't want to put extra digits in a number that you don't know reliably. So that's basically the rules for significant figures. So there's a bunch of rules here, which I'll go over just by looking at examples rather than reading them out loud. So let's look at some examples here. So again, the idea here is that whenever someone is writing down a number, the assumption here is that they are confident about what they have written down. So if someone has written down the number 137, then it means that they are confident in all those three numbers. And so you can ask, how many significant figures are there in this number? The answer here is 3. The rule here is that all non-zero digits are significant. So they would not have written this 7 down unless they really were confident in it. What about 1007? That does involve 2 zero digits, right? There's 1007. But in this case, the 2 zeros are sandwiched between 2 non-zero numbers. And so we say that they are significant. So we say that there are 4 significant figures in this. So that's the second rule. All zeros between non-zero digits are said to be significant. And then what about this number here? This is 0.014. And here we say that the number only has 2 significant digits. The rule here is that all leading zeros are not significant. By leading meaning These two are leading zeros because they're zeros before any non-zero digit. And you can see why this is, these two zeros are not really considered significant. In some sense, they're just telling you a little bit about the units, right? So let's say this was 0.014 meters. Let's say that that's the measurement of some length, but that is really the same as 1.4. No, sorry, let me go the other way. I want to go from meters to centimeters. So let's multiply this. Let's do a little review of units here. If I want to convert this to centimeters, then what am I doing? I'm saying that there are 100 centimeters in 1 meter, right? And so the meters cancel, and you multiply this number by 100, and you will get 1.4 centimeters. So it's the same number. And you can see here that there are two significant digits. Yeah.
I assume this wouldn't work every time, but for a version like that, could you just like move the decimal over 2 places? I assume that wouldn't work for everything, but
That's exactly what we did, right?
yeah, like instead of having to write out the thing, you just see, okay, we're converting it there, move 2 decimal places.
Well, I would phrase it differently. This is what you are doing. And the effect of this is that you could have a mnemonic that you just move the decimal over 2 places. But the real reason you're doing that is because you're doing the conversion from meters to centimeters, and so you're multiplying it by 100 centimeters over 1 meter, which in this case is like move the decimal over by 2. So you can see in this, the same number, the same measurement. If I quote it to you in centimeters, it looks like 2 significant figures. And so therefore, when I quote it to you in meters, it should also be 2 significant figures. These leading zeros are just a matter of what units you're using, for example. And we don't keep track of significant figures here in this factor. This is all exact because by definition, 1 meter is precisely equal to 100 centimeters. There's no uncertainty there. So we don't keep track of that at all. Any questions on that? Okay. What about this number here? This is 5.000. We do say that this has 4 significant digits because these are trailing zeros after a decimal point. So this person who wrote down 5.000, they really mean it. They really know that this number is 0, this number is 0, and this number is 0. As opposed to say 5.001, they're saying, no, it's actually 5.000. Any questions on that? So trailing zeros after a decimal point are said to be significant. All right. Now there's one case where there is an ambiguity, which we resolve by picking a convention, which is that if I have a number, a whole number like this, 5,000, here there's no decimal point. So these are trailing zeros, but they're not coming after a decimal point. And in this case, there is an ambiguity because the question here is, was this number rounded to within the nearest 1,000? For example, maybe this number is like 5325, but you're not quite confident to the nearest 1,000. So you run, it's about 5,000. You're not really confident in these digits. Or did you really mean to say it's exactly 5,000? That these zeros really are there. And the way we resolve this ambiguity is we use scientific notation. If the situation is that really you're nearing it to the nearest 1,000, you're only really confident in the 5, and then you're not sure about the remaining zeros, then what you do is you write this same number as 5 times 10 to the 3, and then you see that this is just one significant figure. If, on the other hand, you are confident about this 0 here, the first 0, but you're not confident about the remaining 2 zeros, then you will write this number as 5.0 times 10 to the 3. So then you have 2 significant figures here. And similarly, if you're confident about these two, then it's 5.00. That's 3 significant figures times 10 to the 3. Or if you're confident in all of them, then you will write 5.000 times 10 to the 3. Any questions on that? So by convention, trailing zeros in a whole number are interpreted as not significant. So by convention, if someone just writes down 5,000, then we say that really this is the same as 5 times 10 to the 3, only one significant figure. Because if they really meant to indicate that all of these zeros are significant, then they would not have written 5,000, but rather they would have written 5.000 times 10 to the 3. Any questions on that? Now, having said that, I think WebAssign doesn't follow this rule, so that's why I'm not too concerned about significant figures, unless the question is about significant figures. Okay, so that was an exercise where there's a number, and then we're just counting how many significant figures there are. But here we will go over the rules for significant figures in multiplication and division. So for example, if I have two numbers and I want to multiply them together, then how many significant figures should I keep in my multiplication answer? So for example, let's say we're making an area measurement. The length is measured to be 2.12 meters and the width is 1.8 meters. What is the area, which is length times width? It's the product of the two, right? Length times width. This is the area. And now the question here is that this number, the length, is measured to 3 significant figures, 2.12, whereas the width is only measured to 2 significant figures, 1.8 meters. Maybe there was a couch in the way and they couldn't quite measure the width as properly as the length. Just trying to imagine a scenario here. So then the question is, in this multiplication, how many significant figures should I keep? The rule here is that you keep the number of significant figures in the answer will be equal to the number of significant figures in the number that has the smallest number of significant figures. So that was a lot of words. But here, 2.12 has 3 significant figures, 1.8 has 2 significant figures. So that means I should only keep my answer to 2 significant figures. Same thing with division. If you were to put this into a calculator, you would get the result 3.186000. That's what the calculator will spit out. But the point is that you really don't have a claim to know that you are confident in this 1 and this 6, because when you do this multiplication, you're not confident in this extra digit here. So that means you're not confident in the 1 and the 6 here. So you only keep the 3.8.
So it's the lowest amount of significant figures.
That's right.
2 things.
It's the lowest, yeah, exactly. If this thing came out to be, if this thing came out to be, say, 3.89, something like that, 10 something, then what you would do is you would round it up. And so you would say that to 2 significant figures, this is 3.9. Over here it was 3.81, so you were rounding it down to 2 significant figures, that's 3.8. Any questions on that? Okay. The rules for addition and subtraction are a little bit different than the rules for multiplication and division. And here the idea is that the focus is on the number of decimal places instead of the number of significant figures. So the number of decimal places in the result of additions or subtractions is equal to the smallest number of decimal places in any term, the least accurate term. So for example, here, this thing has 3 decimal places, this thing has 1 decimal place, this thing has 0 decimal places. And so therefore, your final answer should have 0 decimal places. And again, you can kind of see this just like the multiplication division. If you were to do this addition and subtraction, you would have, for example, 2.127 minus, you would have 6.8, and then you would have plus 25, and then you would try to get the answer for that. But now notice, you're not confident in this number, you're not confident in that number, and over here, you're not confident in this number, or this number. So when you're doing this addition, you're doing 7 plus a number you're not confident in, blah, blah, blah. So you can't be confident in this number, you can't be confident in this number, you can't be confident in this number, so you only keep these two the numbers to the left of the decimal. So that's sort of the logic. And you can do a similar thing what we did for multiplication division earlier. So again, the calculator here will give you this crazy number, 20.372000, but you would only keep it as 20. All right. Okay, so let's do a quick quiz here. I'm going to switch to Top Hat. Start presentation. So here's the question. The number of significant figures in this number is which one of the following? We got 60 seconds. Oh, looks like everyone got it. So let me just go ahead and see what you got. And 3 is indeed the correct answer. And again, the logic here is, well, there are 3 non-zero digits. Every non-zero digit is a significant figure. Well, here's another question. Let's do. How many significant figures in this number? Ten seconds. Okay. And the correct answer is indeed 2. And again, the logic here is that you don't count the zeros because they are trailing zeros. And so only 7 and 2 are significant. All right. Any questions so far? Any questions from anyone on Zoom? Okay. Next, I'm going to switch gears. So that was the end of significant figures. And we'll switch gears here and talk about a new topic called dimensional analysis. And this is a fancier way of saying checking units, but let's go through it carefully. So recall that we had said that in mechanics, there are three fundamental quantities: length, mass, and time. And all of the other physical quantities that we will try to measure or think about will be some combination of measurements of length, mass, and time. So for example, the speed of an object is the distance it covers in some time interval. So you're making a measurement of length and a time interval. And so speed is a derived quantity in terms of these three fundamental quantities. And so what we will do here is we will say that I will let L here denote the symbol for the quote unquote dimension of length. And then I will say that M here is a symbol for the dimension of mass, and T here is a symbol for the dimension of time. So what do I mean by that? If I talk about the speed of a car, maybe that's the next slide, in fact. So if I talk about the speed of a car, it is the amount of distance that it covers over some time interval. So I would say that the dimensions of speed are length over time, or L over T. Those are the dimensions of speed. These dimensions, length, mass, and time, can be measured in different units. Length can be measured in meters, kilometers, feet, etc. And same thing for mass and time. So this is the difference between units and dimensions. In some sense, the dimension of an object is telling you its character, like its length or its length over time. And then when you say meters per second or meters, then you're specifying units in which you are talking about that quantity. So this is the usual notation we will use. If you have some quantity, like length or velocity or acceleration or force, then when I put these little brackets around it, that refers to the dimension of that quantity. So sometimes I may ask you, what is the dimension of some quantity? And then you can tell me, well, speed has dimensions of length over time. If I ask you, what are the units of speed in SI, then you would say it's meters per second. So, dimensional analysis is very useful to check the correctness of equations. So another way of saying this is check your units. So if you write down an equation and the dimensions or the units of the quantity on the left do not match up with the dimensions of the units of the quantity on the right, then you know that there's something wrong in your calculations. Another really useful benefit of dimensional analysis, it is often used by engineers and scientists in the development of theoretical models of various systems. So for example, if you're an engineer trying to describe water flow from some tank or something like that, then you're trying to get the flow rate or something. So you will say flow rate has some dimensions. I don't know how many gallons of water per second, for example. Then you want to, so that's like, that has dimensions of volume over time, which is length cubed over time. And then you want to see if you can build a model for the flow rate. You might try to build a model saying, well, the tank has some volume, the tank has some area, it has some density of material. So you can write down all these different things that the system depends upon. And you could try to build something that has dimensions of flow rate. That can be your first guess in trying to determine, you probably have other physics principles and engineering principles you will apply to it. But you can imagine that you're working to a system where you don't know much about it. Often a first attempt is to build something out of quantities that the system depends on that has the right units for the thing you're trying to describe. And then you put in some parameters and you try to fit it and see if it gives you a good description. Let's get some practice here. So again, length, mass, and time are the fundamental quantities. So if I ask you what are the dimensions of the area, it is length squared, because you're making a measurement of width times length, so it's L times L. Volume has dimensions of L cubed. Speed has dimensions of length over time. Here's an example of a very simple equation where you can check that the left side is equal to the right side in terms of dimensions or units. So here is an equation that's saying that the distance traveled by a car is equal to its speed times the time. So imagine that you were, a primitive caveman and you didn't know much mechanics or anything. And you were trying to build a model for how fast, I don't know, a cheetah is running or something that you're trying to catch. And you will say, well, the ones that move really fast seem to cover more distance in a given time. So maybe let me say the distance traveled is proportional to V and proportional to T. And maybe you don't know maybe there's a number here that's 3.5 or something. You don't know ahead of time yet. But you will say, well, let me just at least check in this model that I have the right dimensions. So here's how you can do that. To check the dimensions, it must be true that the dimensions of distance must equal the dimensions of speed times the dimensions of time. So if I go ahead and do that, the dimensions of distance is just length. The dimensions of speed is length over time. And the dimensions of time is just time. And so you see that the time dimension cancels out, and the left side has dimensions of length, and the right side, in fact, does have dimensions of length as well. Maybe the primitive caveman was attempting a model first where he was like D equals V squared times T. Let's say he tried to do that. Then you would see that the dimensions wouldn't work because this will have dimensions of length, but this will have dimensions of length over time squared, and then this will have dimensions of time, and then this would be length squared over time, and this is not equal to the dimensions of length. So therefore, the cave person will be like, well, maybe if I take away the square and I just write it in a linear dependence, then at least the dimensions work right, and then you have something to work with. Any questions on that? Okay. And this is equivalent to checking units because you can express in SI units, length will be meters, and then this will be meters per second times second. The seconds will cancel, and you'll have meters times meters. But checking dimensions is sort of independent of what units you're using, but they are equivalent. Okay. Any questions on that? All right, I'm at the end of this. Let me switch here. Correct. All right, so here's a quick quiz, which I can't remember if this is a top hat question or not. But before I get to top hat, let me talk about this a little bit. So here is an equation. So again, we are here actually trying to build a model. And we're saying that suppose that the distance traveled by an object is related to the time that it travels according to this expression, where I have x is equal to some constant b times the time squared. So in other words, in 1 second, let's say b is 1, just for, let's say b is 1. Then in 1 second, the x will have traveled 1. In 2 seconds, it will have traveled 4. And you have to, figure out the right units or whatever. So let's say that that's the model that we have. For this equation to make any mathematical sense, you can see right here, this has dimensions of length on the left, and the time here, time squared, has dimensions of time squared. So clearly they don't match. So this constant b here should have the right dimensions to make the left side equal to the right side. And so that's what this question is asking. It's saying, what must be the dimensions of B in order for this equation to at least be dimensionally consistent? And to give you a little foreshadowing, this is actually a real equation that we will come across a little bit later on. And this constant B will have a particular interpretation that we will also talk about in a minute. So with that in mind, any questions about the question? The question is, work out the dimensions of B in order for this to make sense. Okay. So here's the question. All right, 10 seconds. Okay, let's see what we got. Okay, and D is in fact the correct answer. All right, so again, the logic here is that this has dimensions of length, and then you have here the dimensions of B, and then this has dimensions of time squared. So you solve for the dimensions of B as being length over time squared. Anyone happen to know of a physical quantity that has dimensions of length over time squared? It'll turn out to be acceleration, as we will see later on. Right, the acceleration is when people say some car can go from 0 to 60 in 5 seconds. What they're saying is it can go from 0 to 60 miles per hour in 5 seconds. So if you look at the dimensions, 0 to 60 miles per hour has dimensions of speed, that's length over time. In 5 seconds, that's length over time squared. So that's acceleration. So we will in fact see later on that this equation here will end up being 1/2 AT squared for constant acceleration. Highly non-trivial, but by dimensional analysis, you could think about, oh, what must this B mean? What does this quantity B mean? It seems to have dimensions of acceleration. Okay. All right, so I'm going to switch gears again. So we're done with significant figures. We're done with dimensional analysis and units. The next thing for us is coordinate systems. And here, the idea is that we want to be able to describe, in the early part of this course, we will be really focusing on describing the motion of some particle or some car or whatever, some object moving through space. And in order for you to describe it, you have to build a coordinate system so that you can keep track of the car and make measurements and things like that. So, in this coordinate system, there's a few things that a good coordinate system requires. One is it requires a fixed reference point O called the origin. So this origin here is the thing relative to which you are measuring all the distances. So that is like the ground zero. That is the where your x and y coordinates are 0. And then you will have a set of specified axes or directions with appropriate labels. So here, let's construct this two-dimensional coordinate system. There will be an x-axis and there will be a y-axis. And then along these axes, you can make these little tick marks. So this is x equals 1, 2, 3, 4, 5, etc. And this is y equals 1, 2, 3, 4, 5, etc. And then you can see here that this origin will have coordinates of x equaling 0 and y equaling 0. So that's your x comma y. Your origin is 0, 0. And so a point over here, for instance, this point Q has coordinates -3 and 4. And the way you read that is that the x coordinate is -3. So you start at the origin. You go 1, 2, and 3. You go 3 units to the left of the origin. And therefore, it's -3. And then you climb up 1, 2, 3, and 4. So that's 4 units. It's +4. Now, this -3 and +4, where do these signs come from? They come from the convention that you decide which is what you're calling your positive direction. So in this case, the positive x direction is to the right. This is the positive x direction. And the upwards direction here is your positive y direction. Now, what do I mean by positive x and positive y direction? The positive x direction is the direction along which your x tick marks are increasing. So if I'm going in this direction to the right, then your x tick marks are increasing 1, 2, 3, 4. If you start here, it's -3. It's -4, -3, -2, -1, 0, 1, 2. So it's always increasing your x coordinates as you're going to the right. So therefore, I say that that is my positive x direction. Any questions on that? On the other hand, I will say that this to the left is the negative x direction. Negative x direction. Because that is that if you walk along the negative x direction, then your x tick marks will decrease in value. And so, as we will see, often what you want to do is when you're dealing with a physics problem, you will often want, when you're building a coordinate system, you will want to decide for yourself which is the direction you're going to call positive. I could have built this coordinate system in the other way, where, for example, the left was the positive x direction. If I were to make another coordinate system here, this is my x and my y. So by the way, I should say often the way we denote this is we say that to the right is the positive x and to the upwards is the positive y. I could have made another coordinate system where I say that to the left is positive x and to the upwards is positive y. If I were to build a coordinate system like that, then this would be my origin, 0, 0. And then I would have here, this would be 1, this would be 2, this would be 3, this would be -1, and -2, and -3, and so on. So because I've said that towards the left is my positive x, my x tick marks have to be arranged so that they're increasing as you go to the left. Any questions on that? Okay. And then, yeah, so any point in space now in this two-dimensional coordinate system can be given an address with coordinates x comma y, which basically means that you take x steps along the x-axis and y steps along the y-axis. So if it is -3 and 4, then it means that you take 3 steps along the negative x direction, and +4 means you take 4 steps along the positive y direction. Okay. And then finally here we have another coordinate, another way of giving the address of a point, which are called polar coordinate systems. So again, you could have, like this could be like your usual x-axis here and your y-axis here with your positive x and your positive y. So if I have a point here with coordinates x comma y, then one way, then the address that I'm giving you is that you will take x steps along here, and then you will take y steps along there. So I could do something like this, where this is y steps here, and this is x steps there. Right? That's how you get to that point. I can give you the address of that same point in a different way. Rather than giving you the x and y coordinates, I can give you the r and theta coordinates. And here is the rule for using the r theta coordinates. Is first off, we define this positive x-axis here. We call that the theta equaling 0 degrees reference line. And then we measure positive angles by going counterclockwise. So if I tell you that a point has an address of r comma theta, then what it means is r here is like the distance from the origin, and theta here is the angle relative to the reference line. So what I would do is I would, let's do green here. I would take r steps along the theta equaling 0 reference line. And then once I'm here, I've taken r steps here, then I will increase my theta coordinate by keeping my r fixed. So I will try to go along a circle like this, where at every point here, this is a distance r and this is a distance r. So I'll just keep increasing my theta coordinate and then I'll arrive there. So you take r steps here and then you rotate by an angle theta and you will arrive at that point. So two different ways of giving you the address of that same point. So the x, y are called Cartesian coordinates. The r comma theta are called polar coordinates. Any questions on that? Let me, in the last 4 minutes, to just start on a little bit of trigonometry review. So the first place trigonometry will arise is basically in this relationship between the Cartesian and the polar coordinates. So I'm giving you the address of the same point in two ways, x and y, or r and theta. So obviously there should be a relationship between x, y, and r and theta. Actually, let me see. I got 2 minutes left. Maybe I should just stop here and we'll start trigonometry in the next class. All right, let me go ahead and stop the recording.